Hello, every teacher. My name is Chenyang. I come from Wuyi University. I'm also an intern in Institute of Computing Technology, Chinese Academy of Sciences. My supervisor is Jianfei Shen. Today, I will introduce the paper. The title of my paper is A Shallow Convolution Network-Based Contextual Attention for Human Activity Recognition. My speech consists of the following 4 parts: background, methodology, experiment, and conclusion. In the first part, background. In this slide, we will introduce the activity recognition method based on wearable device. What is human activity recognition based on wearable device? HAR is widely used in activity tracking, anomaly detection, and disease warning. We place wearable inertial measurement units (IMU) on human body to collect human activity data. Then, we processing the raw data to a signal image. Finally, we send the signal image to the neural network classifier to classify the user's activity. In this section, we describe how to recognize activity from raw signals. Firstly, we upload IMU data of wearable device to computer. Then, we use a specific window to convert the activity signal into a signal image according to the duration of activity. Finally, we send the signal image to the neural network classifier to obtain the human activities. The above is the overall process of HAR. In this section, we will introduce the related works of HAR. The first method is come from 2019 IGCAI. This method is the combine of CNN and LSTM. The LSTM is used to capture the long-range dependency in spatial dimension and temporal dimension. The CNN is used to capture the local spatial temporal feature. The advantage of this method is modeling the long-range dependency. The disadvantage of this method is LSTM will repeatedly model noise, such as irrelevant signal. The second method is CBAM-based method, as far as we know. The CBAM attention is widely used in computer vision area. This method embedded the CBAM attention with CNN baseline network. The spatial attention block in CBAM is used to capture large-scale spatial temporal feature. The channel attention in CBAM is used to establish the cross-channel dependency. The advantage of this method is modeling the advantage of this method is large-scale spatial temporal features can be extracted and channel correlation can be established. The disadvantage of this method is large-scale receptive fields cause feature compression for low-dimensional data. The third method is come from ECAI 2020. This method is embedded self-attention with CNN baseline network. The advantage of this method is modeling the local global signal correlation. The disadvantage of this method is self-attention mainly relies on the isolated query key correlation to generate an attention matrix. In this part, we will introduce our methodology. In this section, let us rethink the traditional self-attention. We generate queries, keys, and values through input feature map multiple the embedding matrix respectively. We can obtain each embedding matrix by 1 multiple 1 convolution. Then, the relation matrix through K multiple query. The final output matrix is obtained by multiplying the value with the relation matrix. Then, we will introduce our methodology. The traditional self-attention mechanism establishes signals temporal and sensor channel correlation. However, our correlation of query K pairs is in the traditional self-attention are learned on independent query K pairs, which ignore the abundant contextual information between neighborhood Ks. The contextual information is significant to signal feature extraction in sensor signal, which extract local temporal and sensor channel correlation in signal context. In order to solve this problem, we propose a novel attention mechanism named contextual attention (COA), which can combine contextual information exploit with self-attention mechanism in a unified framework. Firstly, COA mechanism utilizes group convolution with K multiple K kernel size across all the neighborhood Ks in K multiple K signal feature in order to specially contextualize each K representation. The contextualized local K represent the local contextual information, which capture local signal feature change. Secondly, we concrete the local K and query, which is followed by 2 convolution operation with 1 multiple 1 kernel size. So, we can make the local signal feature and the global signal feature folds. As described above, global K can capture the signal feature's global information. Therefore, we call the global K as the global contextual information of signal feature. The result of our COA mechanism output is the fusion of local K and global K. Next, in this section, we will introduce the implementation steps of COA mechanism. Firstly, is local K generation. The COA mechanism uses K multiple K convolution to contextualize Ks to capture contextual information between Ks. Secondly, global K generation. The COA mechanism combines local K and queries to form weight metric. Then, we use the weight metric multiple values to form global Ks to strengthen global information. Finally, local K and global K combination. After above steps, the local K and the global K are obtained. We combine the local K and global K as the final attention weights. In this section, we will introduce the backbone network. As this paper aimed to investigate an attention mechanism to augment the convolution feature for HAR networks. We take 3-layer CN architectures as baseline network. Then, we embedded the COA mechanism with CN HAR network to demonstrate the method effectiveness. We also use the 3-layer ResNet as the baseline network and embedded the COA mechanism after the first layer. Each layer in ResNet has 2 convolution processes. Each shortcut connection contains a convolution operation. We gave the specific implementation steps of COA and embedded the COA mechanism into the CN baseline network, as is shown in this slide. Next, In this part, we will introduce our experiment. In this slide, we will introduce our dataset in our paper. We use 5 datasets in our method. The briefly description of the operation for each HAR dataset is shown in Table 1. In this slide, we will introduce the comparison experiment and application experiment. Firstly, Table 2 shows that COA plays an important role in establishing the correlation between local signals and global signals. Secondly, compared with multiple source method, our method has significantly improved the classification accuracy. Next, in this slide, we will introduce the visualization of the HAR classifier. We're comparing the COA HAR method with the baseline CNN for 2 similar activity, going up and walking. It is clear that the COA HAR method had fewer misclassifications. Next, in this slide, we will introduce how the value of K influences the accuracy. For running or falling, the signals are periodic and transient. Although the large K value can extract a large range of contextual information, it will introduce irrelevant signal features. Next, in this slide, we will introduce where is the best position to insert COA mechanism. The result is shown in Figure 8. The COA mechanism should be added after the first, second, and third layers for maximum efficiency. It is due to the fact that high-level contextual information is encoded after the convolution process. Finally, in this part, we will introduce our conclusion. We have 2 conclusions, as is shown in this slide. The COA-HAR exploits the neighbor case contextual information to guide self-attention to capture more correlation informations of signal feature context. Secondly, the experimental results show that the COA mechanism is crucial for increasing the performance of CNN architecture. That is our speech. Thank you for your watching.